Okay, so I'm not going crazy. We are training a multi-class classifier here, just like the binary, except there's more than 2 outcomes. So let's do our best to follow along from where we are. We've split the data into training and testing at a 80-20 split. All right, so we're going to use our functions from our libraries because we don't want to write them ourselves. We could. It's not that difficult, but why reinvent the wheel? If you're curious as to how they work, we can talk about that later. All right. Final step is to make predictions on our test data. To do so, execute the following script. So what are we doing here? What are we doing here? Well, we have initialized a classifier, a multi-class classifier with our argument 5. So we're talking about our 5 closest to whatever we're looking at. All right, cool. Now what does it want? It wants to train. I'm not going to ask you to tell me what kind of flower this is if I don't give you training data. So I'm going to train it. I'm going to train it on our input and our output. All right, it is now trained. Now what's next? Is our classifier done? Well, no, because we haven't tested it. It's all trained and stuff, but do I know it's ready to go out into the real world? Don't know yet. So what I'm going to do is I'm going to, instead of feeding it some data with the correct output, I'm going to feed it some data and see what it says. All right, so let us predict using our X test data into our new variable here. And let's see how it looks. Remember the confusion matrix we had before? All right. So remember that things on the diagonal are talking about, we've got 3 classes. And in each direction, we got our confusion matrix here. Well, I guess this is the confusion matrix, and this is more of telling us what it means. Everything's spot on. Precision and recall, accuracy, everything's literally perfect. So either we did a completely good job, the data is good, which is not that surprising considering that it's 1, well-known data, and 2, we're just testing it, or somehow we've managed to mess everything up completely in every column. I'm going to go with the first assumption, mostly because I've run through this already and it worked just fine. Okay, so remember that the confusion matrix and things like precision, accuracy, these all have solid definitions, and I believe Lab 22, I'm pretty sure it was the last one we did. We also had the F1 score, which is the most commonly used metric. So F1 score is good. All right, let us visualize some stuff because that's always nice. So remember that this is a heat map. It's the heat map of our confusion matrix. So question is, what if we had a different value for K? I don't know. What if I go up here, change this to, I don't know, 4? See what happens. Not much changed. Let's try 6. Not much change there either. Now, it seems kind of silly for me to scroll up, change the number, execute everything, and look to see if there's a difference, possibly making a typo along the way, when we could slap the whole thing in a loop. So one way to help you find the best value of K is to plot the graph of the K value and the corresponding error rate for the data set. In this section, we're going to plot the mean error for the predicted values, test set for all K values between 1 and 50. So let's do that. We've got it's not an array, it's a list. It's going to start out empty, and we're going to put stuff into it as we go. And then from 1 to 50, we're going to do what I just did. I'm going to scroll up, change this, execute everything, and instead, we're going to put in a loop. Okay, done. Next step is to plot the error values against the K values. So we're going to see a plot. Now, keep in mind, this is true 0, to 0.035. Of course, all things are relative, but this is kind of small, as errors should be. What this is a plot. I've got my k value, 1, error 0, okay? And I'm going to go along, and for some reason, when I get to 18, my error is, technically, it's infinitely larger than my previous one. I've got an error of 0.03 something. Okay, well, don't want to use that one. I go along, and the error is back to 0. And you can see where it is. Well, just for curiosity, I'm gonna do it again, see if we get the same plot. Sure do. So just from our running it twice, it appears that everything is the same. So this would indicate that there are some k values I would want to use and some k values I don't want to use. All right. Everything above we did in class, so this is what was done in lecture. But how about classifying a new measurement? So this is the third part of using classifier. 1, you train it. 2, you test it. And then 3, you kick it out the door and let it actually go do stuff. So let's kick it out the door and let it go do stuff. What are we going to do? Well, we're going to classify some data. And what does that mean? Well, we're going to give the program some data, and it's going to tell us what kind of flower this is. So let's do that. Our scaffolding might be use a database to train classifier. We did that. We trained our data. Explore the structure of the predictions. So that was I think it's actually, okay, good. It's not in there. The predictions are here. This is our testing period. So this was me saying, I'm going to rip all the labels off and you're going to go tell me everything. These are your answers to the flowers. So, well, I guess it's not yours. It's the classifier now. So we're going to explore the structure of that. And then once we're confident with those two, determine the classification of the following sample. So we've got a measurement for a flower and we want to know what kind it is. So let's do that. This part is done. Cool. What about this one? We want to explore the structure of that. Well, here, first thing I can think of. All right. Is that useful? Has it been explored? Are we happy with it? Oh, we're happy with that. Okay. All right. Fantastic. I like that. All right. So I guess we're done with that. Once we know everything, which we do now, determine the classification for the following example. All right. So how do we do this? What do we do with this? It's some kind of series of numbers. What do I want to do with that? It looks like floats. So given these floats, I want to predict. So how do I do that? Anyone have an idea? Do we have a classifier? Well, we say we do. What kind of thing is a classifier? What did we call it? Don't know. Well, we used sklearn to do some stuff. And then we talked about a k nearest neighbors classifier. And then we fed it a number, did some fit stuff, and then we did some predict stuff. Anybody remember or know where we might need to look to find what variable we put our classifier in? Now the variable is probably going to be an object. Is it this one? Is y underscore prediction? Is that the one we want to use? Let's try it. So y predict. And then we're going to use that for something, don't know what. And then we're going to be using our datas here. So we got a 6.9 and a 3.1 and a 5.1 and a 2.3. Okay, so I don't know, maybe I need to do something with these. What's something I could do to make Y predict work, do some stuff on these? Throw it in the NumPy array. Hey, that could work. Well, first thing I know how to do is let's just put, oh, well, that's neat. I didn't know that Jupyter would let me do that. First thing I'm gonna do is I'm gonna put it in a list. So I'm gonna call this my input list. All right, cool. Commas, hate commas. All right, it's in a list, and let's make a NumPy array out of it. Okay, we can do that. Now, there's at least two ways to do that. Which way do you guys want to do it? I've suddenly forgotten syntax. Totally don't know. We imported NumPy as NP. So at least one of the ways involves that. What might we do with it? Okay, yeah, let's try that. Array input list, and we'll call this, I don't know, NP list. Okay, all right, we got it in a NumPy array. Cool, that's progress. It is no longer fragmented across 4 points. So we have all our data in one spot. All right, so let us do something with it, and maybe Y predict is what we do with it. So what are we going to do? Like this? Does this work? Let's see. NumPy in the array object is not callable. Makes sense, because what kind of thing is print type Y underscore predict? What kind of thing is that? It's an array. It's a NumPy n-dimensional array. So I'm trying to say, hey, array, I want you to work on this array. Well, that's not going to do anything. Why is that not going to do anything? Well, for the same reason that, let's try to illustrate why. I'm going to make an X be a number, okay? And I'm going to have Y be a number, and I'm going to have Z be a number. And I want to add Y and Z. Okay, so here's what I'm going to do. I'm going to say X, Y, Z, right? Well, that doesn't make much sense. Why didn't it work? Why did my X function not work on Y and Z? Because X is not a function. It's a number. Maybe I need to do this, right? Instead of saying X is a function, let's say I see X has some kind of addition method. So I'm going to call my add method, and I'm going to do that. Well, that's kind of weird. It didn't work. Why didn't it work? Why did the integer 5 not have an add attribute? Do I have to import math? I could, but it won't solve my issue here. What I'm trying to get across here, when we imported NP, which is NumPy, NumPy has a function in there somewhere called array. What does it do? It takes a list, makes it into a NumPy array. That would imply that NumPy has this array function. Well, what is X? Rory, could you tell me what X is? Yes, it's an integer. It's a variable, and it has been assigned to be an integer. It is the integer 5. Does the integer 5 have a function called add? No, it doesn't. So if that's the case, I get the same issue when I try to do this. Well, first off, I can't call it. Okay, well, maybe if I do this instead, I need to classify my list. Well, my object has no attribute classifying. This is the exact same thing as my number 5 not having an attribute called add. Well, why on earth would an integer have an attribute called add? That doesn't make any sense. It's not what it's for. It's just a number. What kind of thing would have an attribute called add? Well, I'm sure the math library would. Import math. So let's say math.add 5 and 6. But it actually doesn't, which is kind of funny. Sum, maybe? Nope. It's unfortunate that just a random example didn't work. But the issue we're having here is that we're wanting something to do this. At least I think. We have our data. We have what we think the name should be. But the problem is we don't know what kind of, what are we feeding this to? So we tried yPredict, because I didn't really get a guess, so I just picked one at random. And yeah, you can bet your bottom dollar I picked the wrong one on purpose. So maybe yPredict is not what we want here. So maybe yPredict is not what we want. So what do we want? Well, I guess maybe it might help to say, what is yPredict? Well, yPredict is the result of running predict on x_test. So it's the predictions. Remember when I said I'll put you in the greenhouse with no labels? That's what that is. It's the classifier's answers with no labels. So that's not the one we want. Which one? What do we want? Maybe a data set? Would our data frame be the thing we want to run on? Is the data frame? Well, actually, you know what? Maybe let's just use the process of elimination. It's not going to be any of these. I'll tell you that. What about this one? Can we, URL is a string. Can we do URL.classify? No, not going to be that one. All right. What about this one? It is a list of the column names. Is it going to be this one? What about this one? This is probably more likely than this one. Is our data set, is our data frame going to be able to do classification? All right, you say no. Why do you say no? What makes you think that our data frame can't do classification? Because it's a 50% chance of being right at this point. Okay, well, that's one way to look at it. It's not 50%. There's like 8 more things. So that outlook is useful when you truly don't know. The problem is we should be out of that mindset by now. So the process we're going through here is we've got different objects on the screen. URL, what is it? It's a string. Okay. Names, what is it? It's a list. It's a list of strings. Data set. Now we're getting into something. What kind of thing is data set? Well, it's a data frame. And a data frame truly is an object. It's going to have methods. It's going to be able to do stuff. Question is one of these going to be classified? The answer is no. Why is the answer no? Because it's a data frame. What are data frames good for? They're good for storing stuff like this and being able to describe them and give the head and all kinds of stuff. A data frame is not the kind of thing that does classification. Can anyone tell me what kind of thing would do classification? What kind of thing does classification? Well, let's see. This is a short lab, so I'm willing to go off on this digression because it's an important one. You could say this is the Socratic method, and that I won't give you the answer, but I will get you to the answer. So by the time we're done here, we'll have you guys at the answer. So if we're talking about what kind of thing does classification, what kind of thing does data frames, those have an answer.
Model predict.
Can I do model predict?
Yeah.
Do we have a model somewhere?
Could we do like inputs and then?
Could we do inputs? Okay, well, sure. I mean, inputs to what?
Like, I don't know. I was just kind of researching it online
that's
because
good.
I was confused.
The confusion is better than it is always. Well, it is almost always better to say I don't know or I'm confused than it is to guess. Almost. So the thing we might. So that's a good question. What might we want to be Googling? Well, does anybody know what kind of classifier algorithm we're using? You should. It's the name of the lab.
KNN.
Yes, it is a K nearest neighbor classifier. All right, so we're getting somewhere. So KNN classifier, that is an algorithm. Cool. What else is kind of algorithm that you guys would have used? Linear regression, perfect. Linear regression, it's an algorithm. How many types of linear regression were there? Were there more than one? Or was there only one, or were there more than one? There were more than one. Okay, so if I were to Google linear regression, I would get a whole bunch of stuff. It wouldn't help me out in this situation because I'm using a specific one. So that brings us to the question, which KNN classifier are we using? Now the answer is in the lab somewhere. I'll scroll wherever you like. But which KNN classifier are we using? So that is a similar question to saying what kind of data frames are we using? And the answer to that is we're using pandas data frames. How do I know that? Well, you kind of know when you write the code, I want a data frame. All right, what library do I want to use? I want to use pandas. Okay, so let's ask the same question for our KNN classifier, because once we know this, we can Google whatever we want. So what kind of KNN classifier did we use? Now, we didn't write it ourselves, so it's got to be one of these things. Sklearn neighbors. All right, well, let's go to that. Sklearn neighbors from Sklearn. Nope, not that one. From Sklearn neighbors. Import KNN neighbors classifier. Okay, cool. We're getting somewhere. Now, we can either Google how to do K neighbors classifier, and here's what I would do. K, that's fine. That's what I would Google. We can either do that, or has somebody put together the links to actually figure out what we call our classifier yet? That's fine if we haven't. Totally fine. All right, let's Google it. Okay, this looks like the official documentation. All right, these are the inputs. Here are the attributes. These are remember when I tried to make an integer do addition? That's what these are called. So we're looking for something in here that might actually run the classifying. We got score, got K neighbors, got get parameters. What might actually do our classification? One second, I gotta move my thing here. So what are all the methods we have? So this is the last 10, 20 minutes have kind of been less a lesson in what to do for the classification, more of a lesson in Python. That's important because I can't make my code do something if I don't know the correct thing I'm asking it to do.
Would it be y predict equals KNN dot predict?
Hey, you're onto
test?
something. You're onto something. So I was going to spend a minute explaining what a method is, but you seem to have gone to something. So generally, the methods are the things that your object does. Your parameters are the things you give to the object. The attributes are things about the object, like length, how many, maximum and stuff. And the methods are things the object does. So if I had a math library, a method I might think would be add. Okay. Well, a method we have here is called predict. Predict the class labels for the provided data. Now that sounds like something we can use. So let's do predict. And what do we call our classifier? It's right here, classifier. We called it classifier. So we've got a name. And we've got so that didn't work because it doesn't have an attribute called classify, but we do have this. We do have a predict method. So what did you say you want to feed this?
I said do like y predict equals KNN dot predict, and then inside do like the NP array, I think.
NP array. So you mean this one, right? You want the NP array from our input list?
Yeah, the NP list.
Okay.
Or it just says like X test in that blank, so I'm guessing that's where that goes.
So it's missing a required positional argument X. Now there's two things to do here. One, you could try to fit stuff in there. Let's try that method. What kind of thing do you think the predict wants? Does it want a dictionary of strings?
When I was looking at it, it said KNN dot fit, and then it has like in parentheses X train and Y train.
Okay, so you're taking the other approach, which is looking at the documentation. Either's fine. So predict. What does it want? Well, it looks like it takes only one thing. What does it take? It takes an array-like shape of test samples. So what's an array-like shape? Well, here's one. This is array-like. Question is an NP array-like? Maybe. Of test samples. Well, is this a test sample? Sure looks like one to me. So let's try it, see what it does. Doesn't look like it wants. It wants expected a 2D array and got a 1D array instead. Okay. Reshape your data using array.reshape if your data has a single feature. or array.reshape if it contains a single sample. Let's try both. Just out of curiosity, I'm going to try this one first. Okay, didn't like that either. Now, what the heck's going on here? I'm not going to make you guys guess because this is a little subtle. It expected a 2D array and it got a 1D array instead. Why? What's the problem here? Well, predict, what it does is it doesn't work on one input sample. You don't tell it to what's the prediction of this flower. It's not how it works. What it works on, if we're using like a visual example, I'm not going to hand you a flower and tell you to go. I'm going to hand you a container of flowers and tell you to go. Even if that container holds only one flower, the way that predict works is it works on containers. So I don't think this will work, but it's a little short of syntax, but let's try, see what it does. Hey, it did something. What did it do? Can anybody tell me? Is this what we wanted it to do? Yes. Oh, are we? Is it done? Is the job done?
Probably not.
What makes you say that?
And you
Does it-
could also just put the NP list instead of the input list also.
Probably. Because
Yeah.
remember what I talked about with the containers? It's just, it wants a container. It doesn't want just one object. I think that's the exact same thing we just got.
When I put in the NP list, it gave me, like, it shows the flower right there.
Could you give me the exact syntax you used? I'm going to erase these because we don't need them anymore.
Well, I think that isn't that the flower in the array that you just had?
Yeah, it is.
Yeah, so then technically we did it right because it classifies the flower.
Yep.
Yes. Okay.
I was just trying to get someone to, you don't always know when you're done, right? It could give me a whole bunch of outputs. I don't know. You got to know when it is an expected output. Because remember up here when we were talking about the confusion matrix, is this an expected thing or is it an error? That's a human job. Only a human can do that. So this confusion matrix here, is it okay? Is it not? Yeah, it's fine. How do I know that? Experience. But here, well, I don't know. What's the output? It returns an ND array of shape, number of queries or queries and outputs, class labels for each data sample. So I'm going to hand it a container of samples. And what's it going to give me back? It's going to hand me a container of labels. So I handed you 50 flowers and you handed me back 50 flowers with the labels on. All right, so we handed it one and it gave us one back. Cool. Here's something we could do. Well, I suppose first things first. Did we do this? Yep. Did we do this? Yep. Did we do this? Yep. Hooray, we did it. Now you still have to turn this in with it working, but hooray, we did it. So technically we're done, but curious minds just gots to know. Let's see if we can make this work on some more stuff. Question is, how might I get some more stuff? How am I gonna get more data? Anybody know? There's at least 3 ways I can think of. So the task, I will make a scaffolding also. I can't give bonus credit, but I'm going to call this bonus. You can go ahead and talk while I type.
Okay, you could probably pull it from the table, but you already know the classes from the table, so I don't know if you need to pull it from the table.
That's one of the methods, as I was talking about. Yeah, we already know what they are, but who cares? I'm going to rip the labels off. and let you run on it, see if it works. So that works. So create some new data to test on and feed data to classifier. Okay, so what you said was, let's take some data we already have. Well, I definitely have my training data. What does my training data look like? Looks like, oh, that's my output. So I want, what's this one? Oops. No, it's uppercase, isn't it? It looks like that. That's a whole bunch of stuff. Okay. Will this work? Let's find out. Classifier dot predict x underscore train. Okay, it gave me some stuff. Is it correct? I don't know. Maybe, maybe not. But remember that in the training phase, we actually know the outputs for these. So I can try, I don't know if this will work exactly, because sometimes, how do I explain this? If I compare an integer to an integer with a double equal, it knows what to do. But let's say I have an object that I make in Python. I'm going to call it a D20. Why is it a D20? Because it models a 20-sided die. What if I say, here's two D20s, are they equal? Can someone explain to me how I would compare to see if two D20s are equal? Let's make it D6, easier. Or as easy as it could be as a coin, two sides. How do I compare if two coins are equal? All possible outcomes for each are the same? Yeah, that's plausible. Sure. But you had to actually tell me how I do that. The equal only works for the things that are built in to Python. So if you make your object in a way to where the equal works, i.e. your object is just a list, so we can compare lists to lists, then it'll work. If it doesn't, so let's say you have to actually check the possible outcomes are the same, you have to do something called overloading, meaning you have to tell Python how to make this work. But the reason I went on that tangent is because I don't know if this is going to be, it works for me. So what do we learn here? It didn't actually do what I expected. I expected it to compare the whole thing and either give me a true or a false. But what it did instead was it went to each, no, what, I'll do this again, print this, and then we'll do this. Now there is, all right, that's good enough. So this is a bunch of flower labels. I handed it some data and I told it, tell me what it is. And then we compared it to what we actually know from the data set. So for the first one, in fact, I'll just do both. What was it called? So Y train, right? Print underscore train. Yep. All right. So I have the data that my machine output after feeding it X train. I have the data from the actual sheet itself, and I have a comparison. So for the first one, Iris setosa and Iris setosa. Good job. And that's the same all the way through here, except till we get to, I'm not going to count because it's too hard. Okay, I guess, but might 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 9. That'll be 18. So this is 17. 17th entry. At least I think so. 0. So this will be 16. So let's print this one. 16. And this one, 16. Okay. All right, so on our 16th flower that I ripped the label off, the machine told me versicolor when the label it actually had was Virginica. Now, what does that mean? Well, it means a couple things. Really what we're getting into is this. We're making the actual classification confusion matrix with the F1 score and all that stuff. And that is way beyond the scope of what the exercise is supposed to be. I'm happy to keep going into it. But what I will just say simply is, what does any of this mean? It meant that the classifier we made was so far perfect, blah, 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 blah. Hey, we missed one. We were 15 for 15. Now we're 15 for 16. It happens. It is a classifier after all. You're not always going to get it completely correct. So we're, what, 16 for 17 now? So how many did we miss? 1, 2, 3, 4, 5. 5? And then, I know it's linked, isn't it? LEN 120. So I suppose I don't need the print statement here. Oops, wrong one. So that's our accuracy. So we got a 96% out of getting it. It's not bad. It's an A. What if your program here, what if our classifier is going to be used on phones for people eating mushrooms? It is a, hey, take this out into the wilderness and you're going to eat some mushrooms. And you're going to snap a picture of it and it's going to tell you eat it or don't. If you don't want to eat it, it's because it's poisonous. And it'll kill you. Or it will make you wish you were dead because it hurts so much. Is this good enough? Would you use it? You would? You're brave. I wouldn't. If it's life or death, less than 1% is where I would go. So this 96% is most, well, I'll save that for the most. All right, I have turned exercise 1 into a 40-minute discussion / lecture on a whole bunch of stuff, Python syntax, typing, how to do stuff, and the actual exercise itself. Happy to answer any more questions, but as you all know, I am prone to digression. So we've done what we wanted to do. Anything else anyone wants to do, or questions people want to?
Do we have any labs due tomorrow?
Last week had, let me look. Yeah, there's a take home. What was that? It sounded like someone said something. Yep. For those interested, I believe this was the lab. Yeah, here. This is what I was talking about that explains all the stuff. So accuracy and all that fun stuff. The F1 score, which is here. Okay. Well, I am not getting any more questions. So what I will do for the next 15 minutes is think of stuff to talk about. Let's see. For your presentations and projects, I get the labs mixed up because different people come to different ones. But from what I've gathered, both of them are involving classifiers, which makes sense because it's kind of it's the tool that uses pretty much everything you've learned in the semester. So any questions on that? I'm happy to answer, or try to at least. The answer could be I don't know. So brace yourself for that. I advise make use of the time you have where I'm here to answer stuff. I'm happy to sit here and pontificate about linear algebra if I can think of a good reason to, which shouldn't be hard. So if we look at this confusion matrix here, notice, and feel free to interrupt me with actual questions about stuff you guys need to know, but notice that the only elements of the matrix that are non-zero are on the diagonal. That's interesting. Well, why is that interesting? Because it is called a diagonal matrix. And in linear algebra, you got a matrix. It won't let me make just the regular bars. And you have something called the identity matrix. It is a 1 on the diagonal and 0 everywhere else. This is just 3x3 identity matrix. Why is that so interesting? It's because you can multiply a matrix by this and it doesn't do anything. You get a matrix in, so A times this, and you get the matrix out. So that's cool. What does that have to do with this? Well, they're kind of close, don't you think? If only there were a way to modify my identity matrix here so that this 1 becomes a 9. That's terrible. This 1 becomes a 9, and this 1 becomes a 12. Well, there is a way you can do that. There are a couple operations you can perform on matrices that don't actually mess with things. One of them is you can multiply or add stuff to a column. So I could multiply the first column or the first row by 9. What if I do that? Well, if I multiply the first column, well, this doesn't do anything because it's 0, and this doesn't do anything because it's 0. I said column, I meant row. So that would mean I would get 9. And you know, just like in algebra, there are certain things you can do on an equation, right? You know, you got x, you got y, and it's got a whole bunch of stuff. I can do anything to this left side that I can do the right side. Well, there's another rule in linear algebra that I can essentially do whatever I want, so long as there's a particular property of a matrix called a determinant. If I don't change the determinant by performing an operation, then I can essentially do whatever I want. Well, one of those things I can do is I can multiply a row. Why? Because the determinant involves every row. Same thing, I can multiply a column because the determinant involves every column. So this is a long-winded way of saying that if I wanted to, I could get a 9 here, and I could get a 9 here, and I could get a 12 here. So what does any of this mean? It means that this confusion matrix is just a version of the identity matrix that scales any matrix I multiply by. So what does that mean? It means that what I'm going to get is just going to be A right back, except the rows are going to be scaled by something. You got 12, you got 9, and you got 9. The more you know. So when did we get a diagonal matrix here? Well, every number here was perfect. So what does any of this stuff mean? It means that the ideal situation for getting your confusion matrix means that it is diagonal. I'm sure that was boring, but I think linear algebra is interesting. Let's see, what else can I think of? I could just end the lab early, but I don't want to do that because ideally what I'm trying to do is I'm trying to stall for time that people actually think of questions they want me to answer. Let's see. I think talking about Python would be more useful to you guys than linear algebra. But what can we talk about that I haven't already hammered into your heads? Don't know. Well, here's something we could do. All right. So remember how we changed the k nearest neighbors from, I ranging from 1 to 50? Let's do something else that's similar. Let's change. Could I go over one of the prior labs? Sure. Which one do you want me to go over? Let's change this. Let's change the test size and see what happens. I'm going to make it 50-50. Oops. Singleton array cannot be considered a valid collection. So what did what just happened? I must have overwrote. Yeah, I overwrote X. So I need to go back and do that. Start over. Lab 21, Pearson 3 distribution model. Sure. 1 second. All right, there. That should be better. 0.5. Okay. I'm going to run this one. Oh, same thing. Let's try 0.8. Interesting. What if I do this? Yeah, didn't like that. Okay, 21. Now, what was the reason I got an error here? Well, what did I tell it to do? I told it to go with a 100 and 0 split. That won't work. 21. I think I have that in the wrong folder. There we go. Pearson 3 distribution model. Use our old friend, Control F. All right. So what are we wanting to do here? We are wanting to essentially fill in these values. This was linear regression. And what's the process we use here? Let's see, the first one, we start with that was the logarithmic. Here's the normal one. I think this was in the lecture, so let me look. 21. Lesson 21. AR. Son. Okay. Well, that's nice. Everything is just here. Pearson down here. This one, I believe. That's the log Pearson. All right. Okay, start from there. Get this definition. Get these. Get that. Now this should not. Oh, did I get the wrong one? Is this log? I don't know. I'll explain what all this is kind of doing in a moment. This might be the log one, but I don't have time to do. I might have time to do both, but I don't think I do. All right. So Kapow. Bear grass. Need bear grass. BRGRAS. Definition. Oh, yeah, we need the text file, don't we? All right. Does it up here? Do I have a BAR? Nope, I don't have it. Okay, we can fix that. But I need the actual text file, which is here. Save as. I think that should work. All right, put it here. Okay, try again. Matplotlib, of course. I need to import all my stuff. You know what? I'm just going to start from the beginning, as I should have done. Requests, pandas. All right, I think that should be everything. Okie doke. Yeah, it's the logarithmic. I was kind of going through a rush. All right, so what do we got? Well, we have our function here that this is the logarithmic one, so you're just gonna have to forgive me for that. What are we wanting to do here is we want to do all our work in log space, meaning take whatever I have, apply a logarithm to it, and then when I'm done with it, do the anti-log. What's the anti-log? Well, if I do ln of x, all I got to do is e to whatever that is to get it back. Okay, so that's how I get into log space and out of log space. So I'm gonna do all my work in log space and then I'm gonna take it out. We have our Weibel post position function, which is what we had before. Now we take everything and we're gonna make a collection of stuff and we're gonna fill it up and then we're gonna take the mean and all kind of stuff. I suppose instead of me going through this, since we don't have much time, which questions do you have about this? Because here's the output result. This still is in log space, I think. So what was your question, Jose? I suppose questions we could ask is this a good fit? It's not terrible. It's better than a line I could draw.
I was just having problems figuring out what the code would be for that model.
You mean the code I used to get this?
Yeah.
Okay. Well, you luckily for you, you did see that I literally just copied and pasted everything, right?
Yeah, I saw that. It's just
Okay.
how would you go about like doing the graph for? Would you use the anti-log coding?
How would I do what? Get the graph?
Yeah, because the graph that you have right there, you said that was the log one, right?
Let's see. How do I explain this? I think we did this in a okay, good. All the outputs are still here. All right. Here is the first one we did. Use the normal distribution. We didn't change anything. We just wanted a line. It's not great. It's okay. It's not great. So what we decided to do was go into log space. So this is the same thing, but we're doing all of our work in log space and then we're printing it out. Make sense?
Yeah.
Now it looks kind of funky, doesn't it? What we do now is we do all of our work in log space and then anti-log it to get it back. And this is the result right here. Now what we have here is the same thing. We already did the anti-log here. Now I'll just comment it out, see what it does. All right. This is in log space and hasn't been changed. See how it looks different than this? This is, I'm still doing all the work in log space, but I'm changing it back using the e to the x function.
So then that graph right there would be the correct graph for it then?
For the log Pearson 3, yes.
Okay.
If you want just the regular Pearson, you don't do this. Let's see. Wherever logit is used, comment it out. Which is, I don't see it. It's in here somewhere, but I'm not seeing it. So this logit and anti-logit function are what let us work in log space. If I don't want to go into log space, I mean, heck, I can just do this. Same thing here. So if I make these functions do nothing, that's what I get. Okay. My time is out. Hopefully that was at least somewhat informative. And hopefully lab 23 was good for helping understand what we're doing. I think this is a 0.2. Okay, so that's all I got. I relinquish control. I am, what do they say? You have the bridge.
Yeah, something like that. Arcane Star Trek references. Okay, everybody. Well, have a good Thanksgiving. This lab is intentionally, what you have to do is really easy for this lab. As Josh showed you, literally a line or two of code tops. And we'll see you next week. Remember, next week, the class and lecture is intended for you to present progress reports on your collective projects. I will get the Blackboard configured to accept this lab and whatever is due from last week by tomorrow. And I will set up the project targets also. They're not there yet. And I have something else I've got to do on Blackboard. I can't remember what it is, but it should be working well in time for after Thanksgiving. So again, have a good Thanksgiving, everybody, and take care. Bye-bye.
Thank you.